and welcome to yet another YouTube video. So, chapter 1, force is done. Yeah, very immediate, the very next chapter is work, power, energy. Yeah, again, a very fundamental building block for the entire concept of physics, classical physics. Building on the concept of force, we explore something called work, power, and energy. These terms, I think, we use it very casually in our daily lives, but let's see what physics has to say about them. Yeah, what do these terms mean in physics? Yes, just like force, which was a physical cause that causes something to happen, one of the effects is that things move. Yes, we have seen that force causes things to move. Work is something that which we associate to activity, to movement. Yes, and it's a very special term when it comes to physics. Let's get on with it. So, what is work in physics? In physics, work is said to be done when a body is displaced under the influence of a force along the direction of force. Yeah, what does it mean? Yeah, let's break it down. Work is said to be done when a body is displaced. That means a movement is happening, a displacement is being caused. Yeah, under the influence of force. A force is acting and a body is moving. That is when we say work has been done. Yes, let's see what it means. There is an object and on it a force F acts, displacing the body to a distance, a displacement S. Yeah, so the work is said to be done. In general terms, in very basic terms, when a force applies on a body is applied on a body and the body moves, work is said to be done. Notice that a very special term, displaced, is being used. In physics, it's a matter of language. Yeah, it is displaced and not, the word used is displacement and not distance. Yeah, so distance is the sum of all the path length. The entire path length is distance. However, the displacement for this loop is 0 because the initial point and the final point is same. So, according to this definition, if there is a circular path and an object, a force is applied on the object and the object goes around the entire path and comes back, the work done would be 0 because the displacement is 0. It will be clearer in the following slides. So how do you measure work done? How do you measure something called work? To make it clear, there is no such thing as work done in physics. It is something that out of convenience we have accepted. Yeah, someone sitting at the top has said work done is F into S. Yeah, force and displacement in direction of force. That is why we are studying it as so. Yeah, but it has some very good consequences. Accepting work done to be F dot S or Fs cos theta or F into S makes life for us easier. How? Let's see. Yeah, so how do you measure the work done? The work done by a force is directly proportional to force applied. So work done is directly proportional to force applied and the displacement produced by the force. Notice the use of the word displacement. Yeah, so work is F into S. S is the displacement in the direction of the force. Yeah, so for in this case the person is applying a force forwards F, and the distance moved is also the displacement, let's say S, work done by the man, let's call him Ramesh, work done by Ramesh is force times displacement. Also note one more very important detail, which is influence of force along the direction of force. Along the direction of force. The displacement should be along the direction of force. Only then this is true. If not, then the general definition is W is F vector dot S vector. Dot product is basically F times S cos theta. The component of one vector in direction of the other times their magnitudes. So work done for a general case in which the force and displacement are in the same direction is F into S. Moving ahead. What are the units of work? The formula for work done, which we just saw right now, is force times displacement along the direction of force. Yes, the unit of force is, we all know, is Newton, and the unit for displacement is meter, the SI unit. So the unit for work done is Newton meter or joule, 1 joule, 1 Newton meter or 1 joule. So from the definition itself, 1 joule is the work done when a force of 1 Newton moves a body through a displacement or a distance of 1 meter in the direction of force. In the direction of force. Similarly, for CGS, the equivalent unit is erg. Yeah, so 1 erg is the work done when a force of 1 dyne moves a body through a distance of 1 centimeter in the direction of force. Yeah, in the direction of force. Again, there may be a question of how are joule and erg related. How are they related? Let's find out. 1 joule is 1 Newton is again 10 to the power 5 dyne from our previous lecture, and 1 meter is 100 centimeter. So 1 joule is 10 to the power 7 erg. Moving on. Okay, till now we have seen that the force and the displacement are always parallel or in the same direction. Yes, what if it's not? What if they are not? What if the force acts at an angle with the direction of motion? Let's see what happens. Yeah, let's say the force is applied horizontally at point P on an object. Yeah, and the object moves in this direction. Along PR. Along PR. What is the work done in this case? This angle is theta and the displacement produced is S. What is the work done? The work done, as we said, is the product of force and the displacement produced along the direction of force. So this is the direction of force, horizontal. What is the displacement along the direction of force? The component, let's call it Q. The PQ is the displacement component along direction of force. I'll repeat it. The definition for work done is the product of force times the displacement along direction of force. What is the displacement along direction of force? It is S cos theta. Yes, how? Let's say in triangle PQR, it's a right angle triangle. What's the value for cos theta? Cos theta is base upon hypotenuse. The base is PQ and hypotenuse is PR. Again, we are given that PR is S. Therefore, PQ is S cos theta. The value for PQ is S cos theta. That is, PQ is the displacement of the body in the direction of force, in the horizontal direction. So, the formula for work done will be F times S cos theta. Yeah, let's move on. It will be clearer in the future. So, there are certain special cases in which we are interested specifically to find out the work done. First, when the force and displacement are parallel to each other, like we saw in the previous case, there is an object and a force is acting on it and displaces it horizontally by a distance s, by displacement s in direction of force. So what is the work done in this case? You can see that the force and displacement have the same direction, are parallel to each other. That is, the angle between force and the angle between displacement is 0. Theta is 0 degree. What is theta? Theta is the angle between the force and displacement. So the work done in this case will be F times S cos theta. Theta is 0, cos 0 is 1. So work done is F times S. Notice that it is positive and maximum. Given two vectors F and S, force and displacement, the work done will be maximum only in the case of force and displacement being in the same direction, being parallel to each other. Yes, it's a thing noteworthy of keeping in mind. So work done is maximum only when the force and displacement are parallel to each other. From board exam point of view, it's a very important point to remember. When theta is 0, the angle between the force and the displacement is 0. Let's see other cases. What happens when the force and displacement are perpendicular to each other? This is the object. Yeah, let's say we are applying a force vertically upwards and the displacement is horizontal. What is the angle between them? The angle between them is 90 degrees. The angle between them is 90 degrees. They are perpendicular to each other. So what is the formula for work done? Are they in the same direction? No. So they are at an angle, right? So work done formula is F into S cos theta. Theta is the angle between force and displacement, which is 90 degrees. So the work done is 0, as cos 90 is 0. So no work is being done when the force and displacement are perpendicular to each other. If you are applying a force on an object and the object is displaced perpendicular to it, there is no force done. Yeah, can you give me an example? The example is a coolie. Yeah, so a coolie, he takes a very heavy luggage on top of his head, and if he walks horizontally, displacement is horizontal, work done is 0, because he is applying a force on the luggage. This is the luggage, applying a force always upwards. He is trying to keep it up, push it up, right? And the displacement is horizontal, so the angle between them is 90 degrees and the work done is 0. Yeah, whenever the force and displacement are perpendicular to each other, the work done is 0. So coolie does no work. I wonder why we pay them. The example for the previous case, when can that be? When the force and displacement are parallel to each other. And where have we seen it? the same coolie, yeah, the same coolie, if he has a luggage on his head, yeah, and he goes up a stair, he goes up the stairs, what is happening? His height is increasing, so his displacement is in the vertical direction. Yes, and on the luggage, this is the luggage, he's applying a force upwards, F, and he's displacing also upwards. He's displacing the object upwards, S. So the force and displacement are in the same direction, are parallel to each other, only in the case of him going up the stairs. When a coolie goes up the stairs, what happens? The work done is positive and maximum. Okay, in this case, when he is walking horizontally on the platform, no work is being done. Yeah, the third case, let's see, when the force and displacement are opposite to each other. Yeah, so there's an object and we're applying a force on it, F, but the body displaces in the opposite direction, S. Yeah, so what is the formula for work done? Is F into S into cos of theta. What is theta? Theta is the angle between the force and the displacement vector. What is the angle between them? It is 180 degrees, and cos 180 is -1, so minus F into S. Work done in this case, in which the force and displacement are completely at opposite directions, is minus F into S. And the work done in this case is minimum and negative. Work done in this case is minimum and negative. Where have we seen it? We have seen it with the same coolie. So he has this luggage on top of his head, and if he comes down the stairs, he is going down the stairs, so the displacement is happening in a downwards direction. Displacement is happening in a downward direction. The force applied on the luggage, this is the luggage, the force is being applied upwards, but the displacement is downwards. So the work done is negative. It is negative in this direction, negative in this case. Yeah, F into S, but in a negative sense. Work done is minimum and negative. One thing to note in the previous cases, which I didn't mention, was because it is too obvious, is that work is a scalar quantity. Work is scalar. That is, it has no direction. It can be positive, it can be negative and zero, but it has no direction. It just depends upon the angle between the force and displacement. Great. All the cases that we have seen before was the case when the force was constant. Yeah, when the force was constant throughout, the formula for work done is force into displacement. What about the other case when the force is variable? Yeah, what I mean is, so in all the previous cases, force and displacement, let's say displacement is in meter and force is in Newton, the force was always constant in the entire duration of motion. The force was constant. So F into S is actually the area of this rectangle. This is F and this is S. The area of this rectangle is F into S, which was the work done in that case. Yeah. Now I want to talk about the case in which the force is variable. Force is variable. Let's say the case of a spring. In the spring, the force is linear. Look something like this. Yeah. So how do I find the work done? The work done is no longer F into S, but the area under this curve. Area under this curve. This is the work done. Yeah. So in the case in which force is variable, we would find the area under the curve of the force displacement graph. Now what do I mean by that? If there is a very general, very typical force, very atypical force, let's say something like this, then the work done will be the calculation of this shaded area. This will be the work done. Yeah, very important from a board exam point of view. Moving ahead, work done against gravity. Yeah, work is done by a force. Yes, a force is applied and the body moves, work is said to be done. Correct? So gravity is also a force. The earth is also applying a force on us. So to move around, to move things around, we have to apply a force against gravity. Yeah, so what is the work done against gravity? The problem is, on the surface of earth, let's say there is an object kept. An object is kept, and I want to take it high to a height of h. I want to take it high. I want to lift it up to a height h. How much work am I doing? What is the work done against gravity? Yeah, to do that, we all know that an object is pulled towards the center of the earth by the earth with a force F equals mg. From Newton's second law, we know that force is m into a and acceleration due to gravity is g. So force pulled is mg. Yeah. So to counteract this force and lift it up, we have to apply another force upwards, force due to us, which is in the of the same magnitude. Yeah, we have to work against the force of gravity to lift it up. To lift it up, we have to apply a force mg. Yes, so what is the work done? Work done by us is force times the displacement. What is the force applied by us? It is mg upwards. What is the displacement? Displacement is h upwards, and the angle between the force and displacement is 0 degree. So hence we can use the formula F into S. So work done against gravity is mgh. What does it mean? To lift an object of mass m against the force of gravity to a height h, mgh is the work done. I'll repeat it. To lift an object of mass m up to a height h against the force of gravity, work done is mgh. Yeah. If a man comes down from a certain height using a staircase or along the slope or using a lift, the work done by the force of gravity is same. What do I mean by that? Even if the path, yeah, because the displacement is what we are talking about. We're not talking about distance, right? So if the object is taken up straight or it is taken up in a as random path as possible, the displacement is going to be h only. The displacement is going to be h only. It is the displacement that we're talking about and not distance. Yes, I hope I'm clear. But work is not a quantity which we can physically relate. I'll give you an example. Yeah, there are two groups of laborers who are given the task of making the same home. Yeah, identical homes. One group makes the same home, the same building, does the same work in 15 days. But the second group takes 1 year to build the same house. Whom would we prefer? Yeah, we would prefer the first group of laborers who are doing the same work in 15 days. Yes, so time is also a factor. Yeah, work is being done, but in how much time? Yeah, and that quantity is power. Power is the rate of doing work. What is the time taken to do the work? Yeah. So power is actually the rate of doing work. Work upon time. Yes. The faster a given work is done, the greater is the power. Yeah. Or smaller the time in which the work is being completed, the greater is the power. Yes. So the power depends on time for which the work is done, and it is also a scalar quantity. That it has no direction. Power exists. Yeah. Power doesn't exist towards east or towards west. Right? It's a scalar quantity. What is the unit of power? What is the unit of power? Yeah. Power is, again, recall the definition, the rate of doing work. Work upon time. The unit for work is joule, and for time is second. So the SI unit is watt, 1 joule per second. SI unit is watt, 1 joule per second. And the CGS unit is erg per second. It comes very straightforward from the definition of power. Yes. One more additional unit is useful in day-to-day lives. You must have heard, my engine has is of 4 horsepower or 5 horsepower, 76 horsepower. What does that mean? In olden days, an engine was graded in terms of horses, how many horses. Because traditionally we didn't have engines, we had only horses. Yes. So 1 horsepower is a unit of energy, unit of power, which is equivalent to 746 watts. 1 horsepower is 746 watt. Yeah. And then some more other units are 1 kilowatt, which is 10 to the power 3 watt. Yeah. 1 megawatt, which is 10 to the power 6 watt. 1 gigawatt, which is 10 to the power 9 watts, and so on. You get the idea. Yeah. Very nice. So what is the relationship between power and force? How do I get it? Is there even a relationship? Yeah. This is for a very specific case. A very specific case in which there is an object. Yeah. Force is being applied on it, and the displacement is in the direction of force itself, in the same direction. The first case in which theta was 0. Angle between the force and displacement is same. Let's see. So we know that power is work upon time, rate of doing work. Work is in turn force into displacement in this case, since displacement and force are in the same direction, upon time. Yeah. What is this displacement upon time? Displacement upon time, if you recall, is velocity. Force times velocity. Yeah. So we get another relation. Power is force times velocity. Given the velocity of the object moving, v meter per second, and the force on which is being applied on the body, we can calculate the power. But this is, again, I would like to repeat it, for a very, very specific case in which the force is being applied on the body and displacement is happening in the direction of force. Only then work is F times S, right? So power is F cross V in this case. Moving ahead, from board's point of view, this difference is important. The difference between work and power. What is work? Work is work done by a force. Yeah. So work done by force is product of force and displacement in direction of force. This is what we have already covered. Yeah. But you should have a habit of writing it down yourself. What is power? Power is the Rate of doing work. Work, it does not depend on time. What about power? Power, power depends on time. Power depends on time. What is the unit for work? SI unit is joule, and the SI unit for power is watt. These definitions are enough to and answer the question, what is the difference between work and power? I hope it is clear. I hope it is clear. Then we move on to the next and final aspect, which is the energy. What is energy? Yeah, what is energy? Energy is actually the capacity to do work. Yeah? Even in our daily lives, what do? We call a person energetic depending upon how enthusiastic he is, or how what's his capacity to perform a large amount of work. Yeah, in mechanics also, energy is the capacity to do work. How much work can a thing do, a system do? Yeah, for example, you have this car. hmm? You have a car. How much energy does it have? You have a toy car, right? You must have seen in our childhood, we have this kind of back push cars, which uses a elastic mechanism to store potential energy, and then when left, the car used to move forwards. Yeah, you wind up the key, you wind it up, and then when you leave the key and you leave the car moves forward. Yeah, so winding action of the key stored some energy within it, and with that the car moves forward or work is happening. Hmm? Again, what are the units of energy? Same as work. Same as work. Energy and work are actually the two sides of the same coin. Hmm. So, what is the unit of energy? Joule. Joule is the unit of energy, and in CGS it is erg. Hmm. Again, in atomic physics, when the particles are very small, yeah, and a very small unit is required, then we use something called 1 electron volt. Yeah, so what is 1 electron volt? 1 electron volt is 1.6 times 10 to the power minus 19 joule. It is a good idea to remember it for your board exams. And also there is one more additional unit that you must have heard is calorie. What is a calorie? It's a buzzword in internet these days. So 1 calorie is actually used to measure heat energy is 4.186 joules, or approximately we may use it to be 4.2 joules. 1 calorie is 4.186 or approximately 4.2. Again, here we can use the concept of kilo, giga, mega. Yeah, we get the idea, right? Kilo is 10 to the power 3, mega is 10 to the power 6, giga is 10 to the power 9. Multiply with this and you get that same unit. Great. Again, in terms of the board exam, the distinction between energy and power is very essential. Yeah, so what is the difference between energy? Energy is the capacity to do work. Energy is the capacity to do work. What is power? Power of a source is the energy spent per unit time. Power of a source is energy spent per unit time. You must have seen the wattage on the bulbs, right? 100 watt, 10 watt, 9 watt. 9 watt bulb means what? It spends 9 joules of energy in 1 second. Yeah, so energy spent per unit time is power. Energy doesn't depend on work, doesn't depend on time. Energy doesn't depend on time. You may lose the same energy in 1 second or in 15 years. Doesn't matter. Energy spent is the same. What changes? The wattage, the power. Yeah, depends on time. Depends on time in which the energy is spent. What is the SI unit? SI unit is joule. What is the SI unit is watt. I hope I am clear. Moving on. Yeah, there are different kinds of energy. Yeah, we just learned about what energy is, the capacity of doing work. Yeah, something within me which enables me to do work. That is energy. And there are different kinds of energy. Like, for example, the first one is mechanical energy. What is mechanical energy? It is the energy possessed by a body by virtue of its state of rest or motion. What does it mean? Let's see. Mechanical energy can be classified into two categories. First is potential energy. Second is kinetic energy. Yeah, kinetic energy is the energy possessed by virtue of motion. If something is moving, any kind of motion is happening, the mechanical energy possessed is called kinetic energy. What is potential energy? Is the energy available for work to be done. Energy available for work to be done. For example, if I have a spring, a normal spring, yeah, no work can be done currently. There is no energy stored, there is no movement. But if I compress the same spring, if I compress it and I place a mass here and I let go of the spring, what will happen? It will push the mass downwards. Work will be done. Yeah. So when I changed the configuration, I changed the position. What happened? Energy was stored. A potential energy was stored. In this case, the elastic spring potential energy was stored, and that energy made work happen. That is potential energy. Kinetic is due to motion. For example, a car is moving, or something is rotating. It all comes under kinetic energy. Potential energy is the availability of energy for work to happen. That is energy. For example, a stretched spring, and a rubber band. Heat energy. You all know what is heat energy. The energy released when we burn wood, coal, oil, etc. It's a very commonsensical answer. What is heating actually? When we heat something, the movement of the molecules has become more rapid. Yeah, the rate of movement increases. So maybe if I have, a tea kettle, and I am boiling it, what happens? You will see that after some time the lid will start jumping up and down. Why? Because the water has evaporated and become steam, and steam molecules are hitting the lid, yeah, and moving the lid up and down. So the work is being done. Movement is caused. Work is being done. How? It is because of heat energy. Energy is the capacity of doing work. Work is being done by the heat energy. Yeah. When we burn something, when we heat something, yeah, heat energy is the energy released then. Yes. Moving ahead. Chemical energy. The energy possessed by fuel such as coal, gas, oil, wood, etc. is called chemical energy. No further explanation required. It's very obvious, right? Energy released from diesel petrol can be used to run a car. Yeah, the diesel petrol, they are compressed, they are ignited, they are combusted, and work is being made. We run a car on diesel, on petrol. How? We are harnessing the chemical energy in it to run the car. Yeah, one more example. How do we power ourselves? It's through the food that we consume. Yeah, food that we consume has chemical energy in it. Yeah, and consuming the food, our muscles work. Our muscles work. What is light energy? The energy in presence of which we are able to see. Yeah, very obvious. Example, the sun. The sun radiates light. Without sun, there is no life. Electric bulb, a fire. This video that you're seeing from the electronic device, the LEDs, the LCDs are emitting light. Sound energy, what is sound? The energy processed by vibrating bodies is called sound energy. In actuality, sound is nothing but just a wave, a vibration. Yeah, vibrations are the ones that generate sound waves. For example, our vocal cords. Yeah, our vocal cord is vibrating. My vocal cord is vibrating, which due to which you are able to hear me, due to which this lecture is being recorded. A guitar. Yeah, a guitar. So there is a audio box and there are the strings, right? The strings vibrate. The strings vibrate, and what happens? The vibration is what travels as sound, and we hear it. And we hear it. Are you getting it? Vibrations generate sound, and that is sound energy. Energy possessed by vibrations is sound energy. Very nice. Nuclear energy. Nuclear energy is the energy stored in the nuclei of atoms. The name itself has it. Yeah, and it was discovered that a giant amount of energy and a gigantic amount of energy can be stored in the nucleus of atoms, which, when harnessed, can produce a lot of energy. A lot of energy. In case of atom bomb, in the case of hydrogen bomb, the energy is uncontrolled. We cannot control the energy, due to which an explosion happens. Yeah, but if it is controlled, yeah, like in nuclear fission, then electricity can be generated. We can use that thing to power so many things. That is nuclear energy. Moving ahead, electrical energy. What is electrical energy? It is the energy due to movement of electric charges. When charges move, electrical energy is produced. For example, electricity. What is electricity? Charges flowing. And that electricity powers our fan, our AC, our refrigerator, our phone, whatnot. Right? That is electrical energy. Then comes a very special kind of energy called the gravitational potential energy. What is it? Yeah, potential energy we saw earlier, right? It's a form of mechanical energy, and it means the energy which can do work, which can let work happen. Yeah, by virtue of its change in position or configuration, the energy is stored and work can happen. Yeah, let's see what it means in this context. The gravitational potential energy is measured by the amount of work done in lifting a body to a certain height against the force of gravity. Yeah, you have seen it before, right? There is a plane, yeah, and there is an object. I want to lift it to a height h. I want to lift it to a height h. How much work is to be done? Work done, we have calculated it is mgh. Work done is mgh. How? The object is being pulled downwards. The force is being applied by the force of gravity is mg. So I have to apply a countering force to lift it up. I have to apply a countering force to lift it up by height h. So the work done is force times displacement. Force is mg upwards. Displacement is h upwards in the same direction. So work done is mgh. Yeah, they are saying the gravitational potential energy denoted by U is measured by the amount of work done in lifting a body to a certain height against force of gravity. So the work done is mgh. So gravitational potential energy of this object at a height h is mgh. Let me repeat it. What is ug? Ug is gravitational potential energy. Yeah. So I want to find out the gravitational potential energy at a height h. What is it? It is the amount of work done in bringing the object from the plane to h against force of gravity. So gravitational potential energy of mass m at a height h is mgh. Yeah. Again, it can be positive, negative, or zero. When will it be zero? It will be zero when h is equal to 0, that is at ground. When the object is placed on the plane on the ground, the potential energy is 0. When is it positive? When is it positive? When it is above the ground, right? When it is above, it is positive. And when is it negative? When the point h is below the ground. So if it is to be brought lower, if it is to be brought lower, then h is negative. The potential energy is negative. Yeah, because work is being done not against the force of gravity but in direction of force of gravity. I hope I am clear. I hope I am clear. Ug is mgh. If h is positive, that is above the ground, the gravitational potential energy is positive. If on the ground, it is 0. Lower the ground, it is negative. Derivation of kinetic energy. Personally, what I feel is this portion in the book is not correct. Yeah, but since it is included in ICSE syllabus, I would like to go through it and I would want you to just take it up as it is. Yeah, there is no explanation for it. Yeah, they have tried to justify the formula for kinetic energy. There is no justification for formula of kinetic energy. Kinetic energy is because it is just arbitrarily chosen to be half mv square. It could be anything. Let's see. So kinetic energy is the energy possessed by an object by virtue of its motion, right? So let's say there is a mass m, and it is moving with a velocity v. Yeah, and it is eventually brought to rest. It is brought to rest. That is, it is velocity is 0 in a time t. The time taken was t. Are you getting it? There is an object m which was moving with a velocity v, and force was applied against it, and it was brought to a rest position in which the speed is 0. Yeah, uniformly being the main key. Uniformly. Yeah, what does it mean? What is the initial velocity is v. What is the final velocity? 0. Yeah, what is acceleration? Minus a, because it is retardation actually. Yeah, so using the equation of motion, v equals u plus at, what do we attain? 0 equals v minus at. Implies a equals v by t. The rate of deceleration is v by t. Get it? So what is the force applied? The force applied on the mass to stop it is mass times acceleration. Yeah, is mv by t. This is the force on the object to stop it. Yeah, maybe the braking force or the force against it to stop it uniformly. Now what is the average velocity in this duration? Average velocity is v by 2. It is actually initial velocity plus final velocity by 2, so it is v by 2. Yeah. So distance moved in this duration is distance moved is actually average velocity times time. It is v t by 2. So using all of that, the work done in the entire process in losing this velocity is force applied times distance moved. Yeah. What is the force applied? The force applied is mv by t. What is the distance moved? It is v t by 2. It comes out to be mv squared by 2. Work done in this case is mv squared by 2. Yeah. So mv squared by 2 is the work done by the force F to stop a moving object of mass m and a velocity v. Let me repeat it. mv squared by 2 is the work done in stopping an object of mass m with a velocity v. Yeah. So the energy possessed by the object of mass m moving with a velocity b should be mv squared by 2. Yeah. And this is the kinetic energy. Yeah. That's why kinetic energy is framed to be mv squared by 2. Yeah, but you see, right, we have taken a lot of assumptions. We have taken that the uniform acceleration is happening. Yeah, then we have taken the average velocity formulation, and then we have come to the conclusion of kinetic energy is mv squared by 2. Yes, in actuality there is no justification for it. Yeah, later on Einstein's equation give out a term which proves kinetic energy to be mv squared by 2, but kinetic energy came much earlier than Einstein, right? So that justification can't be used. I hope I'm clear. Yeah. So this is the derivation that you will show in your board exams if you are asked about it. Derivation of kinetic energy. Work energy theorem. It's a very interesting theorem. It states that work done by a force on a moving body is equal to change in its kinetic energy. That we saw here, right? I am doing a work of mv squared by 2 to stop the object. So work done is actually the change in kinetic energy. You will see it here again. Yeah. Measured by the amount of work done by opposing a force which brings the body to rest from its state of motion. This we did in the last slide. Last slide is the same thing that we did. Yeah. So what it says, if there is an object that is moving with a speed u, mass m, we did some work on it and the velocity has now become v, mass m. So kinetic energy initially is half m u squared, and kinetic energy in the final position is, after the work is being done, is half m v squared. So the change in kinetic energy, what is the change? Change in kinetic energy is half m v squared minus half m u squared, which is basically half m v squared minus u squared. Work energy theorem says that the work done on the object will be equal to the change in kinetic energy. Delta represents change. Yeah. So half m v square minus u square. This is the work energy theorem. In the next lecture, when we solve some problems, it will be clearer. Yeah. What is the work energy theorem? Work done on the moving object is equal to change in its kinetic energy. Nothing else. Yes? Okay. We know that kinetic energy is the energy possessed by state of motion. Now, motion itself can be of three kinds: translational, rotational, and vibrational. An object can either translate, rotate, or vibrate. Depending on that, kinetic energy can be translational kinetic energy, rotational kinetic energy, or vibrational kinetic energy. Yeah. What do I mean by translational kinetic energy? The kinetic energy possessed by the object by virtue of its translational motion. For example, there is a car and the car is moving with a velocity v, mass m. The translational kinetic energy would be half m v squared. Getting it? Rotational means what? If there is an object, let's say the earth, this is the axis of the earth and the earth is rotating about its own axis. The kinetic energy possessed in this case is the rotational kinetic energy. Because of the rotation about its own axis. Yeah, like the wheels of the car. Yeah, wheels of the car is rotating about its own axis also. Yeah, so the kinetic energy possessed would be rotational kinetic energy. Vibrational kinetic energy is again the kinetic energy possessed by vibration. Like for example, when the molecules vibrate, the movement produced is due to the vibrational kinetic energy. And it is possible to possess more than one of the energy at a time. For example, the car is translating, right? The wheels are translating, yet the wheels are also rotating. So they are having both translational kinetic energy and rotational kinetic energy. Moving ahead, there is a law of conservation of energy which says that the energy can neither be created nor be destroyed, but it can only transform from one form to other. And it is something very obvious. Everyone notices it and knows it. Yeah, I'll just go through it very quickly. So how does it work basically? When we do work on an object, energy is stored in it. When we do work on an object, energy is stored on it. How? We have a spring. It's a normal size spring. And then we compress it. We compress it and make it small. The energy possessed is due to the work we have done on it. We have done a work to compress it, right? The work we have done has generated and stored the energy in it, the elastic potential energy in it. Yeah. And this energy can again be made into kinetic energy if we place an object here and we let go of the spring, the object will move horizontally. Yeah. Let's see how energy is transformed into each other. Yeah. Potential energy into kinetic energy. I place the object at a height h. This is the earth. And I let go of the object. What will happen? The object will start moving towards the ground and eventually come and hit the ground. So the potential energy here, the gravitational potential energy, which is by the way m into g into h, if this height is h, gets transformed into kinetic energy. The object here is moving below with a velocity v. So potential energy is being converted into kinetic energy. Mechanical energy to electrical energy. When in the hydroelectric power plant, right? So we have a dam. Yeah, the mechanical energy of the water falling rotates the turbine. There is a turbine here. The blades are here. The turbine blades are rotated by the mechanical energy of the water falling, and that generates electricity. What generates electricity? The mechanical energy has been converted into electrical energy. Electrical energy to mechanical energy. It's so simple, right? The fan that we use. Yeah. The fan that we use, there is a switch connection. We switch it on, the electricity flows through it. Yeah. And a rotational kinetic energy is produced. Mechanical energy is produced, which pushes the air down and we feel cool. Yeah, very simple. electrical energy to heat energy. Example is a heater. Electricity is converted into heat energy. Yeah, we switch on the heater and we get the heat. Electrical energy to light energy. The electric bulb. Yeah, electricity powers the bulb and the bulb lights up the environment. Yes, electrical energy to sound energy. Yeah, the phone in which you are listening to the lecture. Yeah, the battery source of the phone or the laptop is converting itself into sound energy through the speaker. Yeah, one more example can be the loudspeaker. Electrical impulses are converted into sound energy. Electrical energy to magnetic energy. What is the example? Example is a solenoid. Yeah, when the electrical energy flows through the coil, an electric field is generated. Electric field is generated. Yeah, so example is a solenoid. Heat energy to mechanical energy. Where have we seen this? We have seen this in steam engines. The coal is burnt and the steam heat energy is used to generate or to move the train forward. Yes. Chemical energy to heat energy. When we burn wood, when we burn coal, and whatnot. LPG, CNG, everything. Sound energy to electrical energy. Example is a microphone. The microphone I am using is absorbing my sound waves, my sound energy, and storing it as electrical impulses for you to listen later. Getting it? Yeah. Chemical energy to mechanical energy. Example is a car, bus, automobile, everything. Yeah, a battery powered car, everything. The car uses diesel, petrol to convert it into a mechanical energy in which you can move. Chemical energy to electrical energy. When we have a battery and I power a bulb and I power a bulb. Chemical energy of the cell is being converted into electrical energy to run the bulb. Electrical energy to chemical energy. Where have you seen this? Yeah, when we charge a battery. You must have seen, no? We charge our phones. How the electricity is being converted into chemical impulses, chemical reactions in the secondary cell to charge the battery and store it. Yes, electrical energy is stored into chemical energy. Light energy to chemical energy. Where have we seen this? We have seen in solar cells. Yeah, in which the sunlight, the solar light, when it falls on the solar panels, what happens? The chemicals, the chemical reaction happens and the solar energy is trapped inside and converted into chemical energy for later use. Yeah, chemical energy to light energy. And when we use the same solar panel to light something at our homes at night, same example. Or example can be a candle. The chemical energy of the wax when burnt is converted into light energy. Light energy to electrical energy. Yeah, when the solar cells, yeah, can be used to power anything, right? Can be used to power anything. The sunlight has been converted to, let's say, a fan or a bulb or a refrigerator, etc. Get it? Heat energy to electrical energy. This term is called thermocouple. Maybe you're not familiar with it. Thermocouple is something in which if it detects heat, if it detects heat, an electric potential is created. Yeah, electric potential is created. That is, it is converting heat energy into electrical energy. And similarly, into various different kinds of energy, the transformation and transaction keeps on happening. But the law of conservation of energy holds true, which is energy can neither be created nor destroyed. It may be transformed from one form to another, but the total energy of the system remains constant. That is, in the entire universe, the energy, the total amount of energy is constant. Yeah, but the form keeps on changing from one to another. Yeah, a last topic for us is to study this conservation of energy in different contexts, in different ways. Example is a swinging pendulum. Yeah, there is a pendulum, and what I did, I have taken it to an extreme position. This is an extreme position in which it's at the side, extreme position, this and this. And I left it. What will happen? It will come to the center, go up. Yeah, at this point the speed is 0. At this point the speed is 0. So the kinetic energy is 0. As it comes down, the speed increases and the kinetic energy becomes maximum at the mean position. This is the mean position. The center position is called the mean position. Yeah, the kinetic energy is maximum because the speed is maximum. Again, when it starts going up, the gravity pulls it down, the speed decreases, and at an extreme position, again the kinetic energy becomes 0. At the extreme position, its height is the highest from the earth, so the potential energy will be maximum. The potential energy will be maximum. At the mean position, the potential energy will be 0 or minimum. At the extreme position, again potential energy becomes maximum. So you can see the change in energy, the transaction in energy that is happening. Yeah, in the extreme position, what is happening? The speed is 0, but the kinetic energy is 0. Yeah, but the potential energy is maximum because of its height. What is happening when it's swinging and coming to its mean position? The speed becomes maximum. That is, the kinetic energy becomes maximum and the potential energy becomes minimum or 0. Again, when it goes to the other extreme position, what happens? It goes up, the speed is again 0 at that position, the kinetic energy is again 0 because the speed is 0, and the potential energy is maximum. So it comes down, kinetic energy increases, the potential energy is converted into kinetic energy. At the lowest point, the kinetic energy is maximum and potential energy is minimum or 0. As it goes up, potential energy is gained and kinetic energy decreases. Yeah, at any point of this entire motion, the sum of potential energy and kinetic energy will always be constant, and that is the law of conservation of energy. The energy of this system is found in two forms. Number one, potential energy because of the height, and kinetic energy because of the speed. At any point, the sum of potential energy and kinetic energy, that is mechanical energy, will always be constant. That is the law of conservation of energy. I hope it is clear. If it is not, rewind the video and go through the section again. A freely falling body. Yeah, so what do I want to study? I want to study an object and it is falling on the ground. This is the ground. This is the ground. Yeah, so it's position A, position B, and position C. Position A is at a height h. The distance between A and B is x. Let's say it's x. Yeah. The object is kept at a height h initially at point A and is left freely falling under gravity. Yeah. First of all, what is the gravitational potential energy at point H? Point A, it is mgh is the gravitational potential energy. What is the kinetic energy? The kinetic energy is zero because the speed is zero. Correct? When it is at a height, when it is at just about to strike the ground, what is the gravitational potential energy? It is zero because the height is zero and kinetic energy is maximum. Kinetic energy is maximum. Kinetic energy is maximum. And we can calculate it. Let's calculate it. So the sum of mechanical energy is here is u k, which is 0, plus u, which is mgh. So at point A, total energy is mgh. Let's see what happens at point B. The distance traveled is x. Right? It falls freely for a distance x. Yeah. So let's use the equation v squared is u squared plus 2as. Yeah. What is v? We want to find out. What is u? U is 0 because the initial velocity is 0. 2a is g, the acceleration to gravity, and s is x, the distance traveled is x. So the speed at point B is root 2gx. Yeah. So the kinetic energy at B is what? Half mv squared is mgx. It is mgx. And what is the potential energy at point B? The height of point B is h minus x. It is mg into the height. Height is h minus x. So the sum of mechanical energy is what? The kinetic energy mgx plus the potential energy mgh minus x, which is mgh. Do it yourself so that you will be able to understand it more. Yeah. And at point C, how do you find the velocity? Let's again use v square is u squared plus 2as, where u is at point A, which is 0, 2g, and h is the total distance traveled. So v is 2gh under root. So the kinetic energy at that point C is half mv squared, which comes out to be mgh. So the sum of mechanical energies is 0 plus mgh is mgh. So you saw that the sum of mechanical energies is being preserved to be mgh. The sum of energies is always mgh at any point throughout the trajectory of the object. Sum of mechanical energy is mgh always. Let's review it again. Once more, let's revise it. How there's an object at point A, it is dropped. There is ground. Yeah. So somewhere in the middle, let's say here, this point B, the distance between A and B is x, and it falls down, and just before falling the point is C. The height of point A is h. This is h. Yeah, let's analyze point A first. At point A, what is the gravitational energy? What is the gravitational potential energy? It is m into g into the height. The height of point A is h. What is the kinetic energy? It is 0 because the speed is 0. It is just left there, right? Okay. So the sum of mechanical energies, I'll just write mechanical energy is U plus K. Potential plus kinetic comes out to be mgh. Okay. Second point, point B. We know that V squared is U square plus 2as. We want to find out V squared. V squared is, U square is 0 because it is left at rest, right? So here velocity is 0. 2gx. X because s is the distance traveled, is x, right? So the kinetic energy turns out to be half m v square. It is mgx, right? And the potential energy is, we know it is mg times the height. What is the height? This is the height. Height is h minus x. mg h minus x. So the mechanical energy is potential plus kinetic is mgx plus mg h minus x is mgh. The last point C. What is the speed here? V square is u square plus 2as. U is again 0. Initially it is 0. 2 into g into h. H is the total distance traveled from A to C. So the kinetic energy is half mv squared. It is mgh. And the potential energy will be 0 because the height is 0. Mechanical energy comes out to be potential plus kinetic, which is mgh plus 0 is mgh. So you can see that at every point of the motion of trajectory, the mechanical energy, the sum of all the energies remains constant. So we have verified the conservation of energy for two things. Number one, a freely falling body, yeah, and number two, a swinging pendulum. In both these cases, we have seen that the energy remains constant. The total energy remains constant. Please go through the lecture again if you're not understanding. It is a very simple lecture, but it may take a bit of intuition and intellect because we are trying to go a bit more deeper into the subject. Yes, if you have any questions, please drop the questions in the comment section or meet me in the class or write to me, whichever is comfortable to you. And thank you. Thank you for listening to me. Yeah. If you have doubt on any of the topics, chances are that if you revisit the topic, yeah, go back and just listen to me again, the doubts will be cleared. If not, contact me. See you all soon.